Howdy and welcome back. So continuing on here, we're going to begin our discussion on exceptions. So exceptions. Exceptions are going to be C++'s means of separating error reporting from error handling in a general way. Just about every kind of error that we will encounter during runtime can be reported using exceptions. Moreover, the neat thing about exceptions is that you can't forget about them. So if you recall, we said, well, the caller could deal with an error. For instance, in this case, I checked to ensure that the valid that I received back from this area rectangle was valid. But if you start thinking about this, you kind of have to know what area rectangle is doing. And you also have to remember that, hey, I need to go ahead and check and ensure that this was a valid value before I go ahead and begin using it. And a lot of times, you might forget to do this, and that could definitely become problematic. So exceptions are going to be if an error arises, it's going to get your attention because it's not going to allow you to ignore it. So you still have to figure out what to do when an exception occurs, and because every exception thrown in your program is going to have to be handled. An unhandled exception will essentially cause your program to terminate, and we'll go ahead and get into what does it mean to throw an exception? What does it mean to catch an exception? How do you handle that exception? And so on. So here's an example of just very kind of focusing on the bare bones of exceptions with error reporting. So we're going to ignore how we handle these errors up front, and instead we'll go ahead and give a brief example of this, and then we'll talk about how we could determine what to actually do when this exceptional case arises. So notice here, my definition has changed ever so slightly. I have included standard library exceptions, which essentially provide us with predefined exceptions that we can use throughout our program. One of them is going to be a standard library runtime error. So in this case, what I can do is that if an invalid value for area is calculated, in this case, a negative error value, I can go ahead and report this error to the user by essentially throwing a standard library runtime exception along with some sort of descriptive string describing what kind of error occurred. Okay, so I'm going to go ahead and show you what happens when this code's executed. So moving over to Visual Studio Code. I have here exactly what was on screen within the actual slides. So if you look at my driver program, you can see here, double is going to be initialized with the value of area of a rectangle with the parameters of 10 for width, 10 for height. And then I'm simply going to output the value that is returned to standard output. My definition of this is going to be as such, exactly as you saw within the slides. I'm going to attempt to compute an area, multiplying simply width by height. And then I'm going to check to see whether or not a valid measure of area was calculated. If area is less than 0, I'm going to throw a runtime error. And in this case, I'll just say invalid area. And I'll show you how you can actually see what the string is when we begin handling these exceptions. But right now, I just want to go ahead and show you what happens. So if this executes, we're going to see that we'll never actually get to this line. Essentially, this will cause us to return from the function here, and we'll have to essentially handle that exception. Otherwise, our program will terminate. But if we do have a value of valid value of area, we'll simply return it to the caller. So going ahead and running this program with valid values, you can see that a correct area of 100 is computed when the arguments to this function are both positive integer values. However, if I go ahead and change this up and I specify -10 as the width, which doesn't quite make sense, how do you have a negative measure of length? Can't. Go ahead and compile this and run it. And you can see here that my program terminated after throwing an instance of a standard library runtime error. What was it? An invalid area was calculated. And then notice here that execution had stopped. Nothing was printed to standard output because nothing was returned from this function. Essentially, This throw statement caused the execution of this function to stop. The stack, as we'll find out a little later in the course, began to unwind, and we started looking for someone or something that could handle this exception. So popping back over to our slides, let's go ahead and look at how we could handle an exception. So we just reported it. And as you notice here, the user, there's no way it can get by us, because if we don't handle it, our program terminates. So the next question is, well, how can we handle it so that our program doesn't terminate, or if it does so in a graceful manner? So just to recap, when an unexpected condition happens, we can throw an exception in our program. In this case, area rectangle will either return an area calculation, or it will throw a standard runtime error with the descriptive string invalid area. In order to handle the problem, we have to indicate that we are willing to actually catch the expression of the type used to report the problem. In order to do this, what we're going to do is first place a try block around the code where an exception might occur. So think about this as we'd like to try to execute this code, and then if something happens, we'll have a catch block which will directly follow, which will specify the types of exceptions that we're willing to deal with. So in this case, the only type of exception that we're willing to do something about is going to be a runtime error. And don't worry about this ampersand or post-fixing the runtime error type. We'll get into that in a little bit, but just go ahead and follow this convention. So looking at how this is written, and what I probably should have done is I probably should have declared area out here, because notice that in C++, curly braces denote a scope, which would mean that our computation of area would not be visible outside the try block. But just to go through here, our try block says, hey, we're going to attempt to assign, in this case, area, the value returned by area of rectangle -10. So this function gets launched up, and we begin our computation. And because we have a negative value specified for width, we hit this condition executes to true. So a runtime error is thrown. Now, what happens is the runtime system knows that an exception has been thrown, and it will begin to look for an exception handler that is able to handle that type of exception. And what you can see here is that this standard runtime error type of exception, we specified that we are willing to handle it as it presents within an exception handler associated with this try block. So let's go ahead and jump over and look at what this happens when we're actually executing live code. Okay, so we're over here in Microsoft Visual Studio Code again. Let me go ahead and clear out my terminal window, compile this, and then we'll go ahead and walk through it together. So up here, I've gone ahead and declared my area. I didn't provide an initializer. I'm going to get a value essentially within the next statement. So I'm going to go ahead and just leave it as empty right now to kind of show the scoping of all of this. Area is going to be visible from its point of declaration within any sort of inner scopes, as long as it's not hidden by a variable with the same name. And then it will be again visible all the way through until the termination of the block in which it was declared, in this case, main. What we're going to try to do is compute and initialize the value of area with the return value from area rectangle with an invalid width measurement and a valid height measurement. We go ahead and pop over to our definition. We can see here that when this function is called, the first thing that occurs is a computation of area. If area is less than 0, in other words, if it's an invalid area measure, we throw a runtime error. Notice here that in the exception handlers listed or associated with our try block, we have acknowledged that we would like to handle the standard library's runtime error sort of exception. So if one is thrown, we will be able to catch it and do something with it. Here, I've determined that a satisfactory value of an invalid computation of area is 0. So I would just assign 0 in the case that a runtime exception arose from our area rectangle. And again, this is just kind of my decision. If the application was different, I might have handled this in a very different sort of manner, but it's up to us as the programmer to determine what occurs in these exceptional cases. What is interesting is after, say, a catch block is executed, we pick up directly after it. So this line here will be executed. So go ahead and running this. We can see that. And I'll go ahead and put out here just to show you that we actually get within this. I guess kind of communicate that. So here, whoops. I can type. What we'll see here is indeed we do catch that exception that was thrown within our area rectangle. It is handled by the exception handler. We've assigned to area the integer value of 0, and we picked up right where we kind of left off. So here's one other thing that I would just like to point out is that the type of exception must match the type of exception that we've acknowledged that we're willing to handle. So this runtime error must go ahead and match with the type of exception being thrown here. Another type of standard library exception is a logic error. So let's go ahead and just see what happens if we do this. And this will be a different family of exceptions that we're able to throw as well as catch. And let's go ahead and initialize this with 99 just to show that well, it won't matter in this case. We'll leave it at that. So redo, compile, run. Notice here that that standard runtime error was not caught because none of the exception handlers matched the type of error that was being thrown. In some scenarios, we might like to specify the types of exceptions that we'd like to handle, such as, say, a logic error, runtime error, or otherwise. And then we might also want kind of a catch-all that will allow us to catch any sort of exception that is thrown. So this is a catch-all, and if an exception that is not handled by any of the other exception handlers, we'd go ahead and this handler would deal with it. So we'll say catch-all. In this case, let's just, again, maybe set area equal to 0 or something. So compiling and running, you can see here that that this exception handler here did kind of serve as a catch-all, and it allowed us to deal with any sort of exception that was not caught by a previous exception handler. So let's go back over to the slides and continue our discussion there. Okay, so back to the slides. So some fundamental questions of exception handling. The first one is going to be, do I have enough information here to decide how to respond to this error? So let's say we're going through our process. Maybe we're attempting to try to index into a vector within one function. And we're saying that, hey, we'd like to go ahead and catch a out of range exception, which a vector will throw if we attempt to access something outside its bounds. So let's go ahead and let me write up some code real quick to illustrate that, and then I'll be right back. Okay, so I know this handwriting is a little funny, but up here I have int main. I declare a standard library vector containing integers. I named it vect. And then I attempt to index into it and get a value using this value at function I wrote. I pass into it vect, and then the invalid index of 10 because this vector was not initialized with any starting values. I have a catch all exception handler within my main function, and it would do something. So we go ahead and we try to execute value at. And again, we'd probably want to preserve the return value if this were to succeed, but we're looking at the exceptional case here. So we go ahead and execute this. We jump into our function, and we attempt to access the vector's value at IDX. The standard library vector will throw an exception if you're using the .at behavior and attempts to access an element that does not exist within the range of indexable values within that vector. In this case, what we can do is we can attempt, or rather actually catch that exception within this exception handler here. We're saying that if an exception arises in the adjacent try block, if it is an exception of type standard library out of range, I'd like to go ahead and do something with it. Now, notice here, we might not know what the user would like to do in this instance. This is a function we've written. We can assume it's library code, and the question becomes, well, how would they like to handle it? Well, we can go ahead and we can go ahead and catch the exception. Maybe there's some cleaning up that we need to do within this function. We'll particularly see a little bit later in the semester when we begin to talk about dynamic memory, where perhaps we might have to deallocate some memory that was allocated. Maybe we want to deal with a file in a special sort of way in this instance. There's a number of various reasons where we could be interested in doing some local cleanup. And then after we've done that cleanup, we go ahead and pass the buck to the caller by rethrowing that exception. At this point, the exception is rethrown. So it's kind of like identical to what happened here, except it's being rethrown from here. So we're looking for a outer exception handler. At this case, we go ahead and return back to main, and we begin looking at the exception handlers there, and we see that this catch-all can handle it. And then at that point, it would be up to the user to determine what they would like to do in this exceptional case. So the fundamental question of exception handling, do I have enough information here to decide how to respond to the user? If not, then what you can do, as we just illustrated here, is you can rethrow the exception. If you do have enough information, you could handle the exception there as we did in our previous example. One way you should never use exceptions is to handle local errors. Exceptions are designed to handle non-local errors. So when you're using them to handle local errors, you're kind of, I guess you could say you're not using them as intended. So let's say within here, I don't know why, but within area rectangle, we take in 2 arguments to initialize our parameters width and height respectively. We have a try block. We attempt to compute an area, and then we say, okay, if area is less than or equal to 0, let's throw an exception, and then we catch it right there. If this is a local error, and if we wanted to handle it in this manner, why not just say if area is less than 0, then area is equal to 0.0. Here in this particular implementation, the error handling and the error reporting can kind of are blending together, and exceptions are really used to go ahead and separate those concerns so that in one case, just like the vectors at, hey, if some exceptional case arises, I'll go ahead and notify the user by throwing an exception, and I'll let them determine how they'd like to handle it. Here, you're kind of just handling it on your own. And in this particular scenario, passing the buck to the user to allow them to decide what they'd like to do in this instance is probably best practice. Now, if you were dealing with, say, something in main, like the command line argument or the maybe inability to open some sort of file that you need right there in that block, then it makes sense there to go ahead and just go, if some sort of condition, print an error message, return. There's no need to separate out the error handling from error reporting in that instance. So with that ado, we'll go ahead and talk about the different kinds of exceptions defined for us in the standard library exceptions. And then we'll move on to a brief discussion of preconditions and post conditions.